Welcome everyone for this new session of the European Non-Associative Algebra Seminar. And so we have Mikhail Ignatyev who will talk to us about the tangent calls to Schubert varieties for Kac Moody groups. The floor is all yours.
Well, thank you very much. I'm very glad to give a talk at this very nice seminar. But please tell me what the time, 1 hour or 1 hour and a half?
If you can try to do it in 1 hour, it would be perfect.
I'll try. Okay. So I don't promise you, but I'll try. Okay. So let me start from the finite dimensional situation. I mean, very classical. So the main field will be C, just C without any exceptions, and let G be just let be simple, semi-simple, simple algebraic group over C, and of course the main example is just SL, for example. So we fix a Borel subgroup B in G. In this example, one of the most natural choices is just the group of upper triangular matrices. And let F be the corresponding flag variety, G mod B. Of course, you can do the same thing for simplicity group or for orthogonal group, but never mind. Okay, now, let T inside B be the maximal torus, and W be the corresponding Weyl group, the quotient group of the normalizer modulo T, Weyl group. Of course, for SLN, we can choose T to be the group of diagonal matrices. And then one can easily check that W is nothing but Sn, the symmetric group on n letters. Okay, so we have a Brouillard decomposition. Of the group G. I mean, so let W dot denote the element corresponding to W in the quotient group. So then we have the following decomposition. The union of double orbits of the Borel subgroup. So we have the corresponding decomposition of the flag variety. B W dot B modulo B, and I'll denote this guy by X sub W. This guy is called Schubert cell. I mean, cell means cell. It's isomorphic to define variety to define space, and its closure is denoted by XW without a circle, and it's called the Schubert variety. Yeah. So it's very important subvariety of the flag variety, and we know, for example, that XW is contained in XV if and only if W is less than or equal to V via the Brouillard order on the Weyl group yes. So, and it's very interesting question when these varieties are smooth, for example, For classical groups, we have very nice and elegant criterion for this question. But one way or another, all Schubert varieties contain the point P, which is just for the class of the neutral element. And it's well known that XW is smooth if P is a regular point. So, which means that XW is smooth at the point P. So it's the most. This P is the most singular point. Okay, but of course, it happens very often that Schubert varieties are not smooth. Then we can investigate not in tangent space, because tangent space and singular point are not very relevant, but in tangent cone. And let's see W be the tangent cone. And cone to XW at the point P. Let me briefly recall what the tangent cone is. There are different definitions of the tangent cone. The most simple is as follows. So we have some variety, and we consider just tangent lines to the point P. Yeah. For example, if our variety is just a usual cone in three-dimensional affine space, then the tangent space at the origin is the whole A3, while the tangent cone at the point P is exactly X. But we can also define the tangent cone using only theory schemes. I mean, so let O be the local ring of the point P, local ring. It's really local. It has just one maximal ideal, M, just the ideal of rational functions which are regular at the point P and equals 0 to at the point P. And you have the following filtration on the ring O. Just by the powers of our maximal ideals. Well, we have the following graded ring, the corresponding graded ring R, just the direct sum of these guys. And by definition, the tangent cone is nothing but the spectrum of this graded ring. And canonically, it can be considered as a subscheme of the tangent space of X. Okay? Any questions? Okay. It's well known that the dimension of the tangent cone coincide with the dimension of the corresponding variety, CP, sorry. CP doesn't have to be irreducible. It can have several irreducible components, but it's equidimensional. So CP is no, why? Why? Of course, not disjoint, but just the union of its irreducible components. Then all of them are equal. Okay. And in some sense, the tangent cone is more delicate invariant, which describe the geometry of the variety X at the point P. So our goal is to study the tangent cone for Schubert varieties. So what the motivation? The motivation is completely not algebraically geometric. It's completely relevant to the representation theory. Namely, let me consider the group U, the unipotent radical of B. For example, if G is a cell, then and B is the group of upper triangular matrices, then you can be chosen to be just the group of strictly upper triangular matrices with the units on the diagonal. Okay, let's denote by Gothic letters or German letters the corresponding Lie algebras. So G is Lie of G, B, Lie algebra of B, and U or M, would you prefer, be the Lie algebra of U. And we can also consider N minus, the corresponding nilpotent subalgebra. Well, then we have a Catan decomposition of G, I mean, B plus N minus. And so one can identify G quotient B with N minus. Yes? Okay. That's clear. But you also have the killing form on G. Killing form on G, which identifies N minus with N star, with the dual space to N. Okay, now the group U acts on N via the adjoint action. Adjoint action. Thus, one have the dual action of U on the dual space on N star, which is called coadjoint. And it turned out that the space played a crucial role in the representation theory of U. Slightly informally speaking, reducible representations of U are in one-to-one correspondence with the coadjoint orbits of U on N star. Well, to be more precise, irreducible unitary representations in Hilbert spaces of U. Okay, so we would like to describe the coadjoint orbits. Unfortunately, it's officially a wild problem, so we can't do this in general. So we would like to have some stratification of this space. We would like to represent N by a union of some U invariant subvarieties. So what do we have? We have that our N star is isomorphic to N minus, which is G mod B, which is clearly isomorphic to the tangent space of G mod B of our flag variety, yes? Furthermore, we have the action of U or even of the whole group B on N star, I mean, which is induced by the usual action of B on N, just by a joint action. But at the same time, we have the action of B on G mod B, which is just conjugation. And it turns out that it is the same action. And it's well known that tangent cones are B invariant. So this tangent cone is a good candidate to be such an invariant subvariety to make our stratification. This line of reasoning was proposed by Alexander Kirillov, the creator of the Hilbert method in the beginning of this century. And so now we're trying to understand, well, which tangent cones we should choose to create such a stratification. And of course, the first question is, given two elements, W1 and W2 in the wild group, why aren't their tangent cones coincide? of course, the first natural question. And even this question is really, really very, very, very difficult. Well, first of all, we have some simple observation. For any W from W, CW coincides with CW inverse. It's very easy to check. It's just a simple exercise. Okay, so let consider the elements for which this is not a restriction. I mean, if W equals W minus 1, so W is an involution. Well, conjecture is as follows. If W1 and W2 in the while group then the corresponding tangent cones do not coincide. Okay, what do we have about this conjecture to the moment? This conjecture was formulated in 2013 by Alexander Panov, my supervisor, and Dima Eliseev, my colleague. And it was proved the same year for types A, N, F4, and G2 by myself and Dima Eliseev. Next, it was proved for the types Bn and Cn in, well, how to say, this paper was had very long published story, but let me tell this year by myself, Misha Bachkarev, and Sasha Shevchenko. And for Bn and Dn, for special cases, for me and Sasha Shevchenko in, how to say, something like that. And what was the main technical tool to prove this? It was so-called Kostant Kumar polynomials, and it's the main object, the main topic of my today topic. And let me introduce these polynomials. There are several definitions of them, and I'll present the very combinatorial definition. So we have phi, our root system of G, yeah. And let H be the Lie algebra of our maximal torus T. So phi belongs to H star by definition. For example, for G equals SLN, H is nothing but the diagonal matrices, and phi can be identified with the following set: epsilon epsi y minus epsi j, where A is less or J, I mean plus minus, where epsi y is just a standard basis standard in Rn. Okay, so one can consider the following thing. Let W be an element of the while group W. We can choose a basis delta of phi, For example, in this case, one can choose delta to be epsilon 1 minus epsilon 2, and so on, epsilon n minus 1 minus epsilon n. Okay, great. And then it's well known that the while group is generated as a group by the reflections or corresponding to these simple roots as a group. So one can represent W as a product of simple reflections. And let me choose such a representation with the possible with the shortest possible length. This representation is called a reduced representation. Reduced. Okay, and then let me consider the following rational function. C small sub W. By definition, it's just a sign. L of W is just the length, just the number of these reflections, just T. Doesn't matter. And multiply by the following sum. And sum is given over R1, RT, well, or all Ri are 0 or 1. And we have the following rational function S alpha I1 to R1 of alpha I1, and so on. So S R2 of alpha I2, and blah, blah, blah. And the last term is S alpha I1 R1 S alpha IT RT of alpha IT. And the sum is given over all such tuples for which S alpha I1 to R1 and blah, 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 S alpha IT to RT equals ID. So this guy is always ID. I understand that the definition is not very reasonable, how to say. Okay, let me give an example. Well, I'll call this function Kostant Kumar rational function. Rational function. Kostant and Kumar introduced these functions near 1995, something like that. They introduced them to investigate cohomology ring of Schubert varieties. But it turned out that these functions are very, very fruitful to study the geometry of tangent cones. Let me give an example. So let G be SL3 of C. Then W is S3, and we have three positive roots: alpha 1, which is epsilon 1 minus epsilon 2, alpha 2, which is epsilon 2 minus epsilon 3, and there's sum alpha 1 plus alpha 2, which is epsilon 1 minus epsilon 3. So let W be the longest element in the while group, which is just the transposition 1, 3. I mean, in two-line notation, 1, 2, 3, 3 to 1. It can be represented as S alpha 1, S alpha 2, S alpha 1. Okay, so now consider possible tuples of ours, which can give us the ID element. So it probably be 0, 0, 0, or 1, 0, 1. 1, sorry. 1. So by definition, CW equals -1 to 3, the length of W, multiplied by, so we have two summands in our sum. The first summand is divided by S alpha 1 to 0 to 0 of alpha 2, and 1 divided by ID of alpha 1. And the second one is as follows. 1 divided by S alpha 1 to 1 of alpha 1, then the following guy, and finally, again, ID of alpha 1. So we have minus of alpha 1, alpha 2, alpha 1, yes. Then S alpha 1 of alpha 1, of course, equals minus alpha 1. This guy equals to alpha 1 plus alpha 2, and this guy equals alpha 1. And we have the following function minus, I don't need parentheses, minus alpha 1, alpha 2, alpha 1 squared, alpha 1 plus alpha 2, alpha 1 plus alpha 2, minus alpha 2. And I have this function. Okay. So, and it's well known that for the longest element in the while group, you'll always have plus minus 1 after multiplication by all positive roots. Okay, why these Kostant Kumar polynomials are important for the study of geometry of tangent cones? Remarkable fact is true. Theorem that CW depends only on CW. I mean, first of all, CW doesn't depend on the choice of an reduced decomposition of W. It's just a well-defined polynomial. And it turned out that when we know CW as a subscheme of the tangent space, then we can, in principle, compute this rational function. Okay, so as a trivial corollary, we obtain the following fact. If CW1 doesn't equal CW2, then the corresponding tangent cones don't coincide. So to prove that tangent cones for distinct involutions don't coincide, it's enough to check that the corresponding Kostant Kumar rational functions don't coincide as rational functions. The title of my topic is Kostant Kumar polynomials. The point is as follows. In fact, one can consider the following set: positive roots such that the corresponding reflection is less or equal to W with respect to the Brillouin order on the while group. Let me define it. I don't know, S of W. And it was proved by Kumar that if you multiply CW by all these positive roots, then you'll obtain a real polynomial. And this polynomial was called by Sarabili a Kostant polynomial, and then this name moved to Kostant Kumar polynomials. So now, if we would like to prove that tangent cones do not coincide, in fact, it's enough to prove that the corresponding Kostant Kumar polynomials don't coincide, or the corresponding Kostant Kumar rational functions don't coincide. Let me say a couple of words about how to prove this for the classical situation for finite-dimensional simple algebraic groups. AN is, how to say, model example. The point is that. So we consider our matrices. To each involution from Sn, so A minus 1, we can assign the corresponding permutation matrix. And the main question is, what is W of 1? And one can prove the following thing, that if W of 1 is 1, then the corresponding, let me denote this guy by dw, then the corresponding Kostant Kumar polynomial, dw, can be divided by all positive roots, how to say, from the first column, epsilon y minus epsilon j. It is a kind of exercise. But if W of 1 equals j, not 1, then dw doesn't divide on epsilon y minus epsilon j. So this allows us to distinguish situations for evolutions with different W of 1, and the most if W1 doesn't equal W2, but W1 of 1 equals W2 of 1, then nevertheless CW1 doesn't equal CW2. Okay, it's really technical, nothing special ideas. We use some other definitions of Kostant Kumar polynomials using so-called nil-Hecke algebras, but that can be done. So in principle, the proof is by induction on n for an, and the same thing can be performed for BNC and Dn, for Bn and Dn, for some class of evolutions, not for all of them, but as my student told me 5 days before, probably this can be done for all evolutions for BNC. So for classical root systems, we can prove this conjecture totally. Okay. For exceptional, we know the proof for F4 and G2, but for E, we have some results, but unfortunately, we can't prove this for all involutions. Okay, but what are possible lines of generalization of this topic? So there are several generalizations of semi-simple Lie algebras or semi-simple Lie groups for infinite-dimensional cases. One of them is so-called finite simple infinite Lie algebras. They were studied in details by Ivan Penkov and Vera Serganova and a lot of other mathematicians. But of course, before them, there was another generalization, very well known, which called Kac Moody algebras or Kac Moody groups. These are infinite dimensional groups which generalize complete groups, and for them all these questions can be asked. So I don't have any time, in fact, but nevertheless, I will not give a general definition because it's really difficult to define Kac Moody group strictly. But let me give an example. Let G be, for example, the group of invertible matrices GL over field of rational functions. Okay, well, just a group. Of course, it's not an algebraic group, but nevertheless, we can introduce the corresponding topology and blah, blah, blah. Okay, it's called the Kac Moody group of type A. Well, GL or SL doesn't matter. Okay, let B be the corresponding Borel subgroup, which is, at first glance, which is very strange, is the set of all matrices from G with entries in the formal Powell series. So G belongs to GLN of C formal power series, and such that at the 0 point, you will obtain the upper triangular matrices and upper triangular matrices. Wait, sorry. Upper triangular. Well, it's called a Borel subgroup of G. And one can consider the corresponding flag variety, G mod B. It can be naturally endowed by some topology and considered as a variety. And so we have exactly, well, first of all, we have the while group. The while group of G, which is nothing but the so-called affine AA minus 1. It can be realized as a subgroup of affine transformations of the n-dimensional affine space. Unfortunately, I don't have enough time to describe, but well, the combinatorial and the group theoretical structure of this group is really, how to say, really well investigated. Let me describe it group theoretically. It's well known that the group is isomorphic to the so-called SN, affine permutations. What it is? It's just the bijections from Z to Z, such from integers to integers, such that for all I, sigma of I plus n equals sigma of I plus n. And so, of course, since we have such a condition, the entire sigma is defined by the images of the numbers 1, 2, 3, so on, n. And we also say that the sum from 1 to n sigma of I equals the usual sum. 1 plus n means n plus 1 over 2. Okay. And to each such a permutation, I mean, this permutation of Z, one can correspond by some rules. Our Schubert variety XW as a subvariety of F, which is G must be, in this case of affine Kac Moody groups. And one can ask the same question. Given W and W1 and W2, when the corresponding tangent cones coincide. Completely similarly to the finite-dimensional case, one can prove that if you have an element W, then the CW coincide with CW inversed. So one can also consider their involutions. And we have the following conjecture for Kac Moody groups. If W1 and W2 are distinct involutions, then the corresponding tangent cones do not coincide. And to be honest, in fact, we will solve this. We would like to solve the following problem: the corresponding Kostant Kumar rational functions doesn't coincide. uh, all definitions can be given in the scheme of Kac Moody groups, completely similar to the case of finite dimensional situation. We also have that if you multiply this rational function by all positive roots, you can also define positive roots. Let me skip this part from this set as W. Then you'll obtain a polynomial. Oh, I'm sorry. Just a moment. I'm terribly sorry. I'll have to interrupt our talk for 2 minutes, okay? In a moment. I'm terribly sorry. Yeah. So is just again a Kostant Kumar polynomial. So you can just discuss polynomials. Okay. What do we have at the moment? In fact, not so much. At the moment, we have the following. If we consider A1 tilde, then, as Sasha Shevchenko, my student, told me, then the conjecture is true. Nothing more. But what now? What we're doing now? So I'm terribly sorry. Let me interrupt our talk for 2 minutes because I need to. Just a moment. Just a moment.
Okay, so let's resume in 2 minutes then.
Thank you. Thank you very much.
Mhm.
Yes, of course. I'll share my notes. Of course. I'll send them probably to Vanya or I can send them at the moment. Okay, so what's our plan? We plan to prove the conjecture for at least for an tilde for a fine Kac Moody group of type A, using the same thing with induction or modular n. The point is that for the case of these affine permutations, of course, you can embed Sn into Sn plus 1 tilde, but this embedding is not so good as for final case, because for this embedding, simple reflections in Sn doesn't go to simple reflections in Sn plus 1. So at the moment, we don't know how to solve this problem, but we hope that we will. So I encourage everyone to join this project, and I'll be happy to answer your questions. So thank you very much.
Okay, great. So thank you very much for being quick to conclude. Are there any question in the audience? So at
Can you?
the moment, oh yes, go ahead.
Yes. Uh, I'm curious. Why do you need the Kac Moody algebra to be affine? What's the importance of it being affine?
No, you're correct. Of course, you don't need this Kac Moody algebra to be affine. These guys can be defined to all Kac Moody algebras, and yes, and the question can be formulated similar for all Kac Moody algebras. But for me, this is just the first, how to say, the first glance for Kac Moody algebras. I didn't work with them before, so I just started with a fine algebra. But of course, the question and Kumar in his paper of 1996 formulates all these questions for all Kac Moody algebras. Of course, not necessarily fine.
Okay, are there? Oh yes, you can go ahead if you have another question.
No, I was thanking Misha.
Great. So, does anyone else have some question?
So let me send
You are still screen sharing, just for information. Yes. Oh, okay.
yeah, I mean let me send this PDF just a moment.
Okay. And maybe you are doing that, can you just maybe give us a quick idea how you expect this case of Kac Moody group to work? Will it be basically the same kind of idea, or um,
I hope that yes. I'm not sure, to be honest, but I hope that yes, because formulations are very similar. So I hope that yes, that they
but so
be.
for example, you say that for the A1 tilde case, it's okay. It's because you were really able to adapt everything to those settings, and the idea is the same as in the finite case.
Frankly speaking, no.
Yeah.
It's just a case by case consideration. So for
Okay.
I1, it's very easy to describe all involutions, to construct the reduced decompositions. It was done by my student Sasha Shevchenko, and he checked case by case that all Kostant Kumar rational functions are distinct.
Mhm.
So let me send. So just a moment. Well, I'm so not.
Well, maybe are there any other question in the meantime? Because
Uh-huh.
if there are none, then maybe you can just do that.
I sent PDF of my notes.
Okay, perfect. Yes, I can see it. Uh,
So in case of any questions, please, I would be happy to answer them.
well, it seems that at the moment nobody has questions, so I'm sure people can just get in touch with you by email if they have questions. You've sent your notes, that's perfect. So let's all thank Misha again for his very nice talk. Thank you very much.
Thank you very much. Okay, bye bye.